All right, so since it's 9, hopefully more will show or however. Otherwise, I know I have, as I've ran this a few times, practicing, I'll be pushing my hours, so I'll get going. So from functional to parallel with stochastic modeling in C++. Real quick, who am I? It was funny because when I put the notes up for this talk, it was like my website suddenly got hits, LinkedIn got hits, and all of that. And if anyone had the joy, for lack of a better term, to go to my website, you will realize I am not a web designer. No two ways about it. But then when I look at Bajarin's website, he gets a lot of hits too. I'm also not a financial consultant. So I've been doing this for going on 8 years. I love finance. It was part of the reason why I really enjoyed getting this job. So I've learned a lot from it. I'll cover some basic instruments because it has to do with our particular product. I'll give a basic amount on interest rate risk. However, I'm not going to sit here and explain to you what a derivative swap is and why cap is better. That's what I depend on financial analysts for when they give me the algorithm. That's a good question. So, like many of you, wear multiple hats. C++ is my hardest, biggest, and favorite. I do some .NET and PHP. And the hat in the middle is the hat we all want. It's the one that's like, I'll do whatever coding you want as long as you're paying for me to sit on the beach while we're doing it. All right. But seriously, so I started working with CUDA, I want to say back in about 4 years ago, about 2011, and started playing with that because we have a financial model, and it was interesting to see what we could do with offloading calculations. CUDA, compared to AMP, from an ease of use, there's just really not a lot of comparison. AMP just makes things so much nicer in many ways. And so about 6 months before CppCon last year, I was working with AMP, continued working with it after the convention, and came up with some changes we were working on, and so kind of put this talk together to go with it. Some disclosures. So I have a day job. The software, the package that I'm going to talk to you guys about is my day job. I work on it full time. However, our company is we work with a lot of big financial clients. And so I'm here representing myself in this case and when I talk about the software. The software is also proprietary, and that presented 2 problems to me. First off, when I started doing my research, because we were trying to add a feature, we were working on the proprietary software. And so as we did testing and comparisons, it was also done on the proprietary software. So where I'd hoped to take and convert that, and I've started converting it to an open source, if you will, set of code that we can demo with. We did not complete it before the conference got here. At the end of my slides, I have a GitHub set up. Once we get back from the conference, which will be here about a week longer, towards the end of October, we'll start posting that code up. And in summary, that code's going to have, as you'll see, I'll talk about 4 different instrument types: loans, investments, shares, and CDs, and what we call borrowings. And the goal is to make sure that we have a good example set using doubles, which I'll also get to, instead of just floats, to be able to look at and use. Because right now, about the best financial sample that I've seen that's open for everyone to look at comes from the Black-Scholes example with CUDA, and it's all floats. That said, the code that's on these slides, there's one that is a little bit more grayed out, but there's nothing that's going to reveal anything. But if you have questions about any of the work that we're doing, I'm more than happy to share with what we have experience afterwards too. All right, so what we're going to cover. First, I'm going to spend a little bit of time. This is the open view of the application when it runs. That there is actually an interest rate graph showing the interest rates from the 70s on up to today. And you can even see in the 80s where everything peaked. The different colors represent the 3-month versus 10 years. And so this is what our application does, is it works with interest rates. Aside from the interest rates that it works with, in general, it's meant to do asset and liability management. And I'll give a bit more details on that in a minute. The application was started back when Visual C++ was its own product. And so part of this talk is, a good portion of this talk is actually about how we've had to work with this legacy code base to try to move it forward. The application is single-threaded, and no, the GUI is not on its own thread. When I started this project about 6 years ago, I wish I'd read Joel on software, he's got an article he put out right about 2000 that was about the Netscape rewrite and why it was such a terrible failure. And one of his biggest things he writes in there is reading code is hard. And I could not agree more. You know, when I started on this, it was a bear to say the least. However, I struggled through it, and as you get through it, I think you'll find if you work on legacy code bases, you can see some beauty in what was done, especially for the time it was done in. So this comes about because we were needing to add a feature. And for us, features come from 2 points of view, either guidelines or return on investment. Guidelines for us is the FDIC suddenly saying, you need to meet this regulatory specific. You need to make sure that you're following some sort of standard. The return on investment was the case of the stochastic algorithm because stochastic gives a set of randomness that isn't necessarily the same as a historical view. And that comes down to the ROI. And so from a business perspective, as much as there's many things we like to code, in the end, many of us have to code what ends up being told to us. You know, you're in business to make money, so the company dictates what your feature set's going to be. The other things that we've ended up working on is better reporting and also finding other types of technical analysis to do. 2 features that we ended up adding this year, which I'll go over a little bit of how we integrated them with the legacy code base. So stochastic. What is stochastic? So in our top left here, we have the historic graph, which is basically a compressed reprint of the one that's run on the front of our model. And that is, like I said, the historical rates for roughly the last 30 years or so. To the right of that, you have a generated random set of rate paths. It's just random generation within a rough range, but completely random. Stochastic kind of takes a little bit of the both because it turns around and uses a factoring method to say, okay, well, what's the value now? What's the chance that it will change up or down by some factor? And then you generate any number of paths to be able to get your sample data. The thing that's interesting about stochastic is if you end up looking in here, you'll see a solid blue line that kind of represents what the average is. And so from an analysis point of view, there's argument, at least from a financial standpoint, of whether or not stochastic really makes sense. Because by the time you run enough random paths, you get back to a basic average in the end. And so would historic be a better thing? And it's always a fun argument to hear around the water cooler when the analysts go back and forth. So, anyway. Certainly.
Can you address the difference between stochastic and, say, implied volatility in the Black-Scholes? Is that similar, related, unrelated?
I would actually return back to my financial analyst for that one. From the stochastic that we're implementing and the way we looked at implementing it, I would say it's similar because you end up having a small bit of randomness that you're applying to whichever path you're using. The Black-Scholes model, as much as we've reviewed it for technique to implement new things, we didn't look at it as much from an algorithm point of view. So projects. I like Shrek. Ogres are like onions. This project was like a really, really big onion because you get your principal that comes up to you and says, we need to add this little feature. It's called stochastic. Just needs to add some random paths. Okay. Well, then you start going back to your code and you start pulling off layer after layer of code to say, well, what is it really going to take to be able to add this to it? And we'll go over some of those pieces as we drill down. But in the end, there was no simple path to adding stochastic within our model. All right, so some background. Purpose of our application, like I said, is asset and liability management. Asset, if you're not familiar, it's pretty simple. You have a financial institution. They have 2 sides. You bring in money to a savings account or a CD. They loan it back out. Assets and liabilities. Loans and investments are your assets. Shares, CDs, and what they call borrowings are your liabilities. If any of you have ever had that bounce check fee, you know that banks make a lot of money off of fees and stuff like that. They also have to account for loan loss. You saw a lot of things fail back in 2008 because somebody didn't put enough loan loss down. One of the big things with our model that we have had to deal with is precision. And so that's where I was saying a little bit earlier, when we went to look at examples of code that's already out there, a lot of things you find are float. They're not double. And when you're talking about billions of dollars of assets being calculated out and following interest rates on a monthly basis, even the rounding difference of how float happens inside of a computer can generate an error greater than $100,000. And so that ended up being a problem, especially when it came down to hardware and what the capabilities are. As we know, AMP will do double if it's available, and AMP will use the best capable device when it's available. But when you started looking at things like CUDA, you really had to get specific cards because most of their stuff is still geared towards floats. So interest rate risks, why are they risky? Everybody understand why interest rates are risky? I'll give the short portion of it. You turn around a deposit in the bank account at 0.25%, car loan goes out at 3.5%. The bank makes the money in between. But what happens if rates go up? Well, if rates go up, now the bank needs to pay you a couple percent more because otherwise you're going to pull your money out and leave. But at the same time, if they're paying you more, they're losing money on that loan that they just made. And it goes conversely if rates go down. They're suddenly not making as much as they were making, but they're necessarily possibly losing you because you were expecting one interest rate, but now you're getting lower. And so our model specifically takes all of the long, short interest rates over the history, 86 total environments, and says, once we load all of your accounts into this software, what happens if the interest rates go up or down? And it calculates every possible scenario across every possible account and generates that data out in a single threaded fashion. And it still does it at least one account per second. So mind you, as I go through about the legacy code of this app, the app is solid. You know, our company is very big on quality. Nothing goes out without a 4-time lookover because you're talking financial data. But there's so much room for improvement, and we'll see some of the places where it's worked really well. The application, as you saw, is it's definitely a dated application. It's Microsoft Visual Studio, Microsoft Foundation classes. The grid that we use inside is Rogue Wave. We use a few other of their controls as well. I had a short lightning talk last year. We found some bugs in the menu items and such, but all great tools. So functional coding. Okay, so it wasn't Lisp and it wasn't Parallel. When I started drawing up the description of the talk, functional was more like procedural or top-down. It reminded me, when I look at our code, it reminds me of what I used to have to write back when we were learning Pascal in high school. There's parts that look like it was all C because, again, it started back when Visual C was its own product. And then C++ came in, and so the programmers back then started using C++, but they were still C programmers, so it still stayed a bit more like C. And finally, classes get added. And when you're talking about a massive application over years of time, when you don't have a complete rewrite, you have this growth of, the new technology comes out, something gets added. Files are first stored in CSV, and then suddenly XML comes out. Now you get data files that are stored in XML. All C++ based, but there are definitely areas where it's grown down. So functional really sometimes just means that you get the right answer when you run it and it comes out reasonably fast, even though it may not be elegant. And sometimes that's what you need to do because you're trying to write code, you have a project, you have to get it out, and you have timelines. As much as you want elegance in your code, you have a deadline that you have to hit that keeps the product on track. So, current issues. A lot of foreground to the talk. We'll get into the actual code and the problems that we've had now. And in hindsight, as I went through this, I definitely found the description may have led more to AMP versus not. I tried to make that the small case because we do have the parallel part. It's about a third of the talk. But there was more in between that. So, globally speaking, we have hundreds of countries around the globe, right? Our application actually has 5 times more globals than countries in the world. And that's been put on a diet. We've cut that back by at least a third in the past 5 years. And those globals are not necessarily elegant. And I honestly didn't understand this one. The first couple of years I was doing it, it took someone smarter than me to help point it out. As much as I've been doing C++ for a while, I have learned under fire at points. But if you'll notice the extern that's defined up there, it causes the whole global file to be externed in a way. And the way it ends up happening, all we can end up doing is using default constructors on all the globals. It won't use any other kind. And that's created problems because there's spots where you're trying to add on a particular feature and you want to use a custom constructor, but in order for other parts of the application to be able to see the code you need, it has to remain a global. And so as much as we want to turn around and add the new features of C++ 11 or 14, it's not always easy when you have a legacy code base to just do it the new way. Sometimes you have to make that patch to keep things going so you can add on something new while still maintaining and having it work with the existing items. And when it comes to globals, size matters. So if you look here, we've got a whole bunch, well, size matters. On the slide here, you'll notice at the top, we've got a bunch of structs, which are actually arrays of structs. And below that, you'll notice that we have integers that are basically reference numbers to the size of those arrays. Don't know how big they are. They get initialized elsewhere. Unfortunately, they are initialized. However, this is the initialization, of one of them. And you'll notice that the initialization starts at, I want to say row 5 up there, row 6, and it finishes down at 329. So that's 324 elements in between. That T-row structure I did a size of, just in a breakpoint, is actually 84 bytes, but those the strings are actually char stars. So even an 84 byte count for one row is generous. I mean, that's small. It doesn't take into account the size of the actual arrays themselves. So this one set of rows represents one of our model types. We have 19 of them. Those were the structs that were on the previous slide. This particular one comes out to be about 27,000 bytes, not counting the data structures inside. Held in global memory all the time. And if you look at the structure that we have here, the way it's set up, I'd like you to pay attention to 2 points because it'll be important later. We have the R name, like R, and you'll see a beginning balance. That's kind of ends up becoming a row definition. The other item that we had to help define the structure is there's a set where you'll see like XXIX inside the quotes, or LIBS. Earlier I mentioned that we have loans, investments, borrowings, or shares, and so that ends up trying to point to a type. This became important when we decided to try to break this out into classes because we have this huge structure here which somewhat symbolizes the index of a spreadsheet. And you'll notice that a lot of this ends up doing that as we go through. And as I worked on this more, we found that a lot of the original programming for the financial analysis started in Spreadsheet and moved forward. So in the end, 27,000 times 19, not counting character arrays. And this is just one small part of the global memory in use. So globals in this way, it's not the best, it's bad. It's not anything that we would do nowadays, but it's how things came up. It's how the code moved forward. No locality. We don't have access controller constraints, and the constraints have definitely nailed us over and over again with debugging. Something being overwritten we recently just solved an issue with that even in the past month because of adding a new feature and having something overwritten. So it's a constant battle. But more so when we're looking at trying to add stochastic algorithms or even multi-threading period, the concurrency issue is big. And so that has ended up being one of the major problems that we've had to work through solving. So an array is technically a data structure, right? You get boxes with an index. It's a data structure, even when it's 630,000 cells long. It's a data structure, not the one you want to work with, but now that's 630,000. So that row structure that we had, that I said, is one model type, that's actually one RAID environment. So multiply that by 86 because we maintain all of these RAID environments on top of that. So if you take the 324 rows we had at 27K bytes, 86 RAID environments, you start to reach almost 2.3 megabytes of memory for one of our models, for one account type. And so then on top of that, you track things out to 30 years, you start looking at almost a gigabyte of memory to manage one model running at a time. And so the part of so we're going to change a little bit here from the fact of we have this row structure that we use to index everything, but we actually came into a fortunate point here because when we have this class called CModel that actually does the model calculation, it actually news up that array I was just discussing. It actually news up a huge array of doubles. At this point, one RAID environment for one account is 87,000 cells. Turns out to be 697,000 bytes when you roll it out by doubles. But it is being created in its own memory. And this gave us a spot of possibility because even though our row indexes were sitting in global memory, we now had the capability possibly to do our calculations on separate arrays. We started exploring this and we haven't taken this too far down the path, and we'll show why in a little bit here. But in general, if you can imagine trying to keep even 100 of these in memory indexed with a row column type of a calculation, it's not a pretty sight, especially if you have to debug. The section below there where you see the define QR names, and at the beginning of the talk I was pointing out where we have the R variables, and that's just pushes along to the fact of this is a row index, it turns it into a number. And so one of my favorites that's been impossible to debug because it's defined as a macro, you'll see that xref. So it actually takes this big array and using the rows from the structure definition plus a column number does, I want to say it's column major conversion to take a single dimension array and make it look two-dimensional. So we have two-dimensional arrays now. But at the same time, when this was first programmed, I can't imagine being the programmer that, one, had to figure this out to begin with, but two, then the fact of we get written code for something that we need, and then how do you carry forward? At what point do you start tearing things out to apply new techniques? And as I considered that even more preparing for the talk, it was like, we had that big lag from 98 to 2011 on C++. And so it makes me wonder, with all the new features that we've got now, all the new revamping of doing better, I look forward to being able to change this out, but I can understand why the original programmers, once they got 2 or 3 accounts in, it never changed. It ended up staying just this way. As I went further in a couple of years working on this, I'd seen a talk someone recommended, and now I can't remember the gentleman that performed it, but basically this has a capability to it though, because it's contiguous memory that's on the stack, and so, stack? I get my stacks and my heaps confused. But it's contiguous memory, and so since you're doing pointer math on it, it ends up being very fast to access. So we have the model as a class, which is called CModels. We have a rough pointer to this data that's called CAccount, but they're 2 separate items completely. The model ends up doing calculations on the data. And when I started preparing for the talk and I was writing up the description of it, I'd made a mention in the talk about looking at multiple inheritance because we were just trying to find a solution to be able to integrate into our current application that was going to be similar to what's there, because in one case, if I'm pulling any kind of a count calculation out, I have to replace it with something similar interface-wise. And it was interesting the comments and feedback we got back about not actually, not attempting multiple inheritance, don't even consider it. And we did find a better way. But when you're trying to find ideas for how to make something work and you have this much legacy code, you look for whatever you can in a way. So we have one method in our calculation that you have all these different financial instruments 4 or 5 of ours are very similar. You know, if you take a loan or you take an investment, they all have interest rates, they all have balances. One, though, might be amortized, meaning, you know, you pay interest every month. One might be single pay, like a balloon loan. But these are just small differences. And so in order to try to consolidate things, they actually made one function that calculates all the models using a nice if-then struct to say, well, if you're a type 1 through 4, let's calculate a 1. If you're a type 8 or 9, then use a different calculate method. And so this is where I was pointing before. It's like they reached the point of C++ and started writing classes, but there wasn't really inheritance. It was still a lot of if structure, still a lot of, you know, the old ways of going about doing things. So once our calculate 01 gets called, it then has another set of case statements and if structures. It says, well, if you're a type 1, you're variable. If you're type 2, you're not variable. If you're type 3, you're fixed. It really makes you want for object-oriented code. I mean, it really does. Because that one method that gets called after this ends up being 400 lines long. And it blurred from 2 points. One, it was 42%, and 2, this one I was asked to blur. It's a huge if-then structure. Anytime we add a new account, you know, if it's suddenly a variable and we need to add a feature into that, well, guess what we just did? We probably created a side effect to everything else underneath of it. Because not only is this structure being used to calculate the type 1 type, as it is, or a loan type, or a variable type, it happens to work for loans, borrowing, shares, CDs, etc. And so the main point of this slide is that, you know, it's a shame that the stuff that we do sometimes carries forward and grows because of deadlines and such. It's hard sometimes to get, you know, the principals or the owner of a company to understand that, listen, I can spend 2 extra weeks now and do this right so that in 3 years when you ask me for another change, I can do it in a week instead of a month. We've made progress in those ways. So math is massive methods. I always liked, someone told me, you know, 15, 25, 35 rule. Keep that many lines in a method or less, and that would be a good way to go. 400 lines obviously isn't that. But our reporting mechanism, we have a class, and I'm showing this one because we did make a big win in this area, and there was a reason to. This class started out, it does all of our reports. We have about 100 or so reports, and we have this method called getReportData. And the line number it starts on there is about 6,099. I collapsed it so you can see the ending line of that method. That one also went on a serious diet. We trimmed about 4,000 lines from it over the last year by actually pulling things out of the case statement and putting them into their own procedures at least. But it literally is a set of case statements that's like, okay, if your case ID is 4001, meaning report 40.1, then you're going to run this set of code. If you're 40.2, you run this set of code. And the code was just strapped in between brackets. There were no procedures. So in a way, aside from debugging this method, anytime we had to add a report, it was cumbersome at best. But then debugging it, going through, you know, you can set breakpoints and stuff, but it's still a lot of code to read through. And from the previous slide, you saw the amount of local variables being started in there as well. 7,412 lines in total. And at one point in time, I do believe it was well over 10,000. So we used to have, yeah.
It also looks in the previous slide that the number of scenarios you have in your Monte Carlo, in your interest rate calculation, seems to be fairly static. Because are those references to specific scenarios?
Yes, so the way our simulation ends up working is we use 86 rate environments. So we have the historical graph that you saw at the beginning, and out of that historical graph, there are, for the most part, 86 environments. And when we look at a rate environment, we take the long and the short. So we'll have a rate environment we'll call, like right now, we're in 0002, because your long term right now is pretty much a 0% government rate. Your short term is roughly a 2% rate. And that's the current rate. And so then it will scale all the way up to 1614, which although has never technically happened, it's, it's one of our extremes, all the way down to 0, 0. And so, yeah, there is at least a static set of rate environments that we process through every time. Of those, 86, 64 we put a special emphasis on because they're what we consider the real environments that have happened, where we use the others for what they consider a shock.
One more question. Do you also calculate the Greeks, including second-order Greeks, in your simulation, or is it just the base option value?
It's just the base, well, so we have the base option value from a rate perspective, but we do give the capability of doing derived rates as well as user-defined rates. And so we have financial institutions that will give us a derived rate such as, based on the government rate, we always charge this, but in some cases, if the rates go up or down, we'll apply a different rate. So I don't necessarily think we do the Greek, but we do end up having customizations to our rate environments that are more specific to the institutions we service. There is no, at this point in time, there is no random inside our model, which was the whole point of looking at stochastic. Everything that we do right now is based on the fixed historic curves and applying forward curves from those. Incidentally, below there, where we see the calculate and print 400 detail row, this was one of our slimming downs, and I want to say that once we pulled this out into a procedure, it probably removed about 500 lines. But anyways, so adding a report. So when I first came onto this company, fortunately they gave me 2 months, but that was my first task to prove to get the job. I had to go through the code with no help, no one to talk to, read it, and add a report to it. And with all the things that we've seen so far, it was definitely a daunting task. My MFC was a little rusty at that point too. But I was really quite proud because after the first year, I got reasonably efficient. And I came up with a document that was in 24 easy steps how to add a report. And I actually given it to a colleague. And the funny part about it is, we have these wonderful descriptions like, okay, well, you need to add an extern int whatever for identifier for the report, and it's around this line, and then you need to go down here and you need to add this particular array because it's around this line, and then what we found was after about 10 or 15 reports, of course the documentation didn't make sense because all the line numbers had changed. It's not like you had procedures for it, so you had to use these kind of line references. Likewise, even though you could stick the definition really anywhere in a header file, then that kind of makes the documentation that much harder on it. And so we were quite happy to be able to replace this with something much better. I'm sorry, did you have a question? Okay. And so that brings us down to roughly the final part of what we're getting at, which was what we've been able to do with all of this. So reporting was, as I mentioned, one of the places where we had a really big win. The slide here, just gives a shot of the different kinds of reports that we have, and most of our reporting is generated out in numbers. We do graphs and things, but when it comes down to what we provide to our clients, numbers are what matters. And so a group inside of our company was able to take the get report data, as you saw there, which was massive, and make it so that we could just extend onto it. Now, the thing that I think was important about this is the company I work for, we do risk management. They are very risk adverse. They don't like change. So when we said that we believed we had a way to implement better reporting, or at least better classes so that reporting could be done in a better way, their first concern was, excuse me, their first concern was the fact of what it would break, because we have hundreds of reports and we just cannot risk breaking anything. And so the part of this that became even better was the way that they ended up making the class C reports DM extendable. It left all of our existing reports working exactly as they did, using that one massive get report data. But it gave us the capability that now we literally just extend a class, fill in the required methods with the customizations we need, and the reports end up showing up. So now we actually have one report per set of class files instead of the 40 reports, which are literally in one file that's 40, 50,000 lines long almost when you put the headers and the CPP together. benefit from an hour point of view, at my best, we used to be able to make a copy of a report in 8 hours when we were using the 24 easy steps, and that was making a copy. That wasn't any customization. That was simply going through all of those steps to put the right stuff in the right spot and copying a data section from another report. Now, last week, we had to add a report, and start to finish, I was able to put the whole report in with customizations in 2 hours flat. It was a pretty simple report from the data we were pulling out, but it was more the fact that items such as menus and titles and all of these things became much simpler. Debugging is by far even easier because of the fact that everything is held within a nice simple class within one file. Globals, they get us all the time, and even now. So as I mentioned when we were looking at the globals, we actually had a variable called G offset, which G being in front of it, all of our globals have a G in front of it. So it should be a global, but it wasn't. And unfortunately, because of the way the new class was, we actually had to reference this offset variable because it helps us get to that PX array. You have to set an offset so you know which scenario am I looking at, which value group do I want to get to. As I mentioned, we have these 86 scenarios, so when you have one account data, that whole column major kind of thing, it says, okay, well, here's your first, 100,000 values roughly for this particular account in rate 1 environment. If you want rate 2, 3, 4, or 5, you have to go down the index. We had the problem that the local definition had to be there from the point of view that we needed to be able to access it in the inherited class. However, by doing that, once it exited the inherited class, it left the offset off, which manifested itself in one single yield value being off by 200 basis points, or 2%. It took almost 48 hours between two programmers to be able to debug it, because even setting memory breakpoints on the values wasn't really the effective way to do it. We had so many RAID environments that you had to go through. It ended up being in one RAID environment that this produced itself. And so I bring that up from the point of view of I really disliked globals at that point in time. More importantly, having a structure instead of an array that's so many cells long where you're having to calculate a manual index to find your value it makes you want classes. So the next big advance we've been able to make is an add-on module which does static analysis. The reason I want to point this one out is from 2 points. First, it allowed us to hang something easily off the side. And so whenever we were considering doing development, it was a question of what can we end up adding, how can it end up accessing things, and how can we make it better than what we've been using before. And so the core application being the type of code it is, whenever we can find something that just reaches in and grabs the data it needs and does it in its own new and better way, we like to do that. As a side note, what we call a static analysis, when you do finance, everybody wants to make money. So whenever you turn around and forecast something, you're typically saying, well, I'm going to make 10% next year, or I'm going to make 20% next year. But from a risk test, you want to be able to say, well, what if you make nothing next year? And what if all you can do is keep your balances at the same condition? And so this worked out well from being able to do as a separate kind of an add-on module, because although it requires some of the same data, the calculations ended up being different. So this is just actually a picture of the slide, which I covered a bit of, but when it came out, we were able to generate really nice classes. We actually now maintain the monthly summary data. So for each month, summary data is held within its own structure, which ends up being owned by the account structure. We end up having a configuration structure that's able to maintain the configuration. So if someone changes the configuration because they want to see some different value, it's held separate from the actual calculated data at the same time. And all of that ends up getting owned by this one class called static balance sheet. This ended up being one of the best places that we were able to first start testing with Stochastic, more so how to parallelize. Stochastic didn't apply as much here because you're doing a static balance, you're not randomizing stuff much, but we were trying to find a way to get the operations to complete faster. And so we finally had a nice set of classes that were easily contained so that I could actually test what can we do to thread this and make it more parallel. And So this turned out to be a good test bed. We started with OpenMP just because it was easy to throw in some of the headers, if you will. I like to call them more. They're not a define, but using some of the nomenclature it has for its for loops to parallelize things. However, it worked really well for parallelizing account calculations, meaning we could parallel and have it say calculate all of account 1, account 2, account 3, and account 4, which was a massive speed up, especially when you're talking going from single threaded. But it still wasn't reaching that plateau that we wanted where you're really calculating fast inside of an account. So back to the implementing stochastic and onions. As you can see from our model structure, implementing stochastic, there wasn't an easy way to do it in a parallel fashion. We looked at being able to parallelize the one data array, and we're actually still trying to figure out a way to do that. We're still where we can still access the indexes of the particular account types while parallelizing more of those arrays in memory. Part of the problem is the data being a separate index. It just makes it difficult to debug. So even when we get 4 or 5 of these running within memory, if we get a value that's not coming out right, trying to go in and debug those 4 or 5 arrays running at the same time is time consuming at best. So then we started looking at, well, what if we do make new classes? And we'll look at those in a minute, but that came back to the part of what are you going to rip out? This is our core loop that we're talking about, so it's not quite so easy just to simply pull apart the way things have been done inside, whereas with the static balance module, we're able to hang it on the side. And then finally, we did get the argument back to what is it worth, because when you look at the stochastic, you end up getting an average in the end. How is that really different? One way that we ended up looking at doing was actually using a spreadsheet to import rate paths, because you can actually generate rate paths outside using other tools. And as we had a model that's already single-threaded and we needed a solution, this was actually looked at being used, because this could generate the rate paths, we could import those rate paths, and then it would go through and calculate. However, like I was saying, our model is fast right now. For the 86 rate environments, it can do an account in 1 second. But if suddenly you're taking those 86 rate environments and doing 1,000 paths per rate environment, you got an overnight kind of a run. I mean, that's back to what it gets to. And that is actually how it used to run when they first developed it in Visual C, but that kind of runtime is just not acceptable in today's world. So we generated new classes. We took those row indexes that we were looking at earlier, and as I'd mentioned, to look at the quote XIXX or the LIBS, so there's 19 of those accounts. It's roughly 6,000 rows of indexes, and a lot of them are very similar. But what we ended up doing was going through and saying, okay, well, which one of these belong in every account? And we started making the C account class with those. Then we broke it down to going, okay, which ones had Bs, which one had Ls, which one had Is. It actually took several weeks to start to, well, I say several weeks, in addition to all the other stuff we were doing, it took several weeks to be able to break these down. In the end, we came up with a 3-tier structure, which we start with a basic account class, which then gets broken out into borrowings, loans, investments. We also have shares and CDs and a couple others. And then finally, we went to another level, which was, okay, well, we have a fixed loan or we have a variable loan. By the time we reached that level, what was interesting is we were now at about a 5% data change, but far more a calculation change. So a bulk of the data still resides in the C account. We have a lot in the base class, but then most of the rest, kind of an 80-20 or more like a 75-20 and 5 dispersion. This class structure, we've had to strip out some of the more advanced analysis, but this is the class structure that we're currently working on to break down a bit more, that will be out on the GitHub towards the end of the month. We will work to make sure that we have one of each account type able to do a parallel run. And so we're focusing first on cash flows with a couple interest rate environments, because we would like to see better demo code out there, even if it's not to a double or a float precision yet, because we haven't seen it. And so we've taken what we've tested in our internal model, and we are working on breaking it out. You'll see more of this out on the GitHub. In the end, instead of having R rows, we now just have doubles. It's also been broken out to where, when we have something that's such as the government rates for 5 or 6 years, we now have a year structure that can actually be used in reference by month if you want. Your yield curves can actually be referenced by the tag of 3 months, 6 months, 1 year. And so from a debugging point of view, and we saw this with the static balance sheet, it's just much nicer to be able to look at something and know what it's supposed to be doing. That point of the expressive code, to have the code document itself. Code that you're sitting there looking up a cross-reference of a row number to a cell number based on an interest rate environment is not really self-documenting. So in testing, for our model at this point, threads and OpenMP are kind of trumping AMP. And it's not anything that has to do with AMP. It has to do with our model code. We're just getting far more speed-ups in our testing by being able to parallelize the data. And that really comes down to 2 points. I believe we will get far more speed out of AMP. However, right now, one of the problems that we run into is the way accounts are calculated. So this is from the static balance sheet. This is one of the row sets of data that we showed on an output earlier. The problem is the yellow lines are the only ones that can actually be calculated in parallel. All the other data relies on a previous month in order to calculate it. And so where we can turn around and run the accounts in parallel, we're still working on design to make sure that we can offload part of these structures at least to be able to calculate, on a cell-by-cell array level versus just parallelizing the accounts themselves. And so at least from our experience in the finance of interest rate calculations, this has been one of the bigger problems. The other problem we have is, as I mentioned in the beginning, is doubles versus float. So floating point computation, if you look at most of the NVIDIA cards, you'll find a lot of them are integer. They have great integer performance. Their floating point goes down. And I was amazed because even the new Kepler cards, they're far more integer-based float than floating point. Whereas, I have a picture of an M2090 up there because I just recently purchased one a few weeks back because I wanted to do more testing. This was one of the last series of cards that still had, I want to say, 600 gigaflops of floating point capability. But even there, it's floating point. It's not double. And so from our perspective, we're still going to continue trying to find the best way to get floating point to work. I say start because we need double. And every time I come back with an example set of numbers from float, usually the analysts are saying, oh, no, you're off by 300 basis points over here. That's not going to work. But I am interested to follow up more on the hardware. AMP gives us that great capability of being able to unload on whatever hardware is available. But I think there's going to be an aspect to it where, depending upon the calculations you're wanting to do, you're going to need to look at that hardware and say, how much can I really throw at you and what are we going to be able to get out of it? So in the end, I wanted to sum up. So out of all the years I've been working on this, I have 6 really solid ones. And so I got a few slides I wanted to sum that up with. My first year, I learned reading code is really hard, especially when you have no one else to compare to and no one else to ask questions of. The amount of time you can spend a debugger will make you want to go to the boss and say, can I please rewrite this? Can I please rewrite this? And fortunately, they always told me no, because I would have had no idea how much I was biting off. The article from Joel, if you haven't read it and you have a legacy code base, it is a very good one to read because one of the things he points out, which I saw even more as I'd worked with the code base, there's elegance in what they did and why they did it. There's bug fixes there that you'd be naive to think that you're going to solve all of them in your first write ever again. It's things you should never do part 1. And so if you look for Netscape rewrite, I think if you Google like Netscape rewrite failure or Netscape rewrite Joel, it should pull it right up. The second year I learned source control was my friend. I mean, everybody knows that, but when you take over a project and the source control is a bunch of separate zip files comprised about every 3-6 months, it makes SVN look beautiful. We use TFS now. I like all platforms and such, so GitHub is great too. Some stuff we'll use Git, but TFS worked well because you get that nice integration of bug tracking at times, and it really helped with our setup. My third year was learning to refactor and repurpose, but not to rewrite. We definitely went through and did a lot of trimming, a lot of bug fixing, cleaned up a lot of memory leaks in the third year. That's when we trimmed out about 500 globals, and we've been trimming ever since. The repurpose I look at from the point that that's where we also started trying to hang modules off the side. Okay, we really can't change the core, but what can we do to continue making this better, using newer technology, and then work backwards when we get the chance to. But don't rewrite. I'd finally learned by then. Tools matter. I liked the keynote speech Jean gave because I really liked the fact of static analysis helped us a lot. Especially with the side of this code base. We migrated up to Visual Studio 2012 by this year, and it had built-in static analysis. So even its basic static analysis that was built in helped a lot. We then used external tools, and it ended up making a big difference. So I'm a big fan of the tools, especially when you look at other items, TFS, etc. Teams are better, and a little C++ is a good thing. We have a project manager who is actually a financial analyst, and he used to give me all of our specs, typically in a spreadsheet, with the calculations in it. And he'd taken a C++ class about, 8-9 years ago when he got his, I think it was an arts degree. But we put the Visual Studio on him, gave him the debugger, showed him how to run it. And what's turned out has been amazing because, in short, he'll give us a spec, we'll code it out, but we'll have a function that's slightly wrong or a calculation that's slightly off. And you guys, if you use Visual Studio, you know that the tools they're nice. You can show someone how to debug. And now all of his financial knowledge will solve a calculation issue in a quarter to a fifth of the time that it used to take us by going back and forth making changes on a spreadsheet. Much to the chagrin of the principals because he spends more time coding now than financial analyzing, but I'm fine with that personally. And it's also from my point of view, as I said, I started learning finance more and more as I've done this, and he becomes better at being able to explain to me why something's wrong. And so I think the part that's important on that is, I know that there's probably far more experience in all of you guys than I have on one finger, and it's that idea that it doesn't even matter if a person's only been coding in C++ for 1 year. If you can look up at my code and tell me you think something's wrong, I want to know. Which leads to that we all help each other become better developers. And most everybody here, I think, already knows that and gets that. That's why we're all here. And so, future items. So again, we're actually here for another week or so after CppCon, but we will be working on putting that demo code up there. And if you're interested in finance and stuff, I'd love to create a dialogue and share information on what we have. Although there's a lot of things I couldn't necessarily give up in our source code to it being proprietary. There's lots of things that we can share and ideas and build on without any doubt. And questions? Yes?
So, first of all, you talked a lot about refactoring and making things better, but I didn't hear anything about testing.
So I don't use testing harnesses personally. I haven't reached that level, I guess you could say. So I'm not of the writing the test harness first. I'm more reactive in testing. But from a testing point of view, the company I work for, when I say nothing goes out the door if it hasn't been checked 4 times, every piece that we write goes through a release phase in testing. In fact, one of the static balance feature that I was mentioning, we actually had to make a cut right before I came to CppCon, and it's been in testing since. And so even while I'm here, I'm getting small, there's a bug. And testing for us ends up being, it's difficult to debug, but it can sometimes be quite easy for the analyst to test because we know what our base was before and it's proven. This was what the numbers were coming out to. And so now whenever we make a new model, we make a cut, we have certain test sets that we feed in, we know what the results have to come out to be, and when you find that one value in the one rate environment that happens to be off by, So we do a lot of testing. I guess you could say it's more old-fashioned necessarily than automated.
And the second question was about the floating points. Did you guys consider using fixed point math instead?
So we have not. And I think primarily because every time I go in and look at the code base, I see double. And anytime I tried to change to float, we'd have a problem. But when you say the fixed point math, that makes me think of how, for example, MySQL changed out of their floating point to using fixed point inside some of their values. So I'd be very interested in learning more about it. I have not touched that yet. Anything else? Yeah.
Can you talk any more about your use of AMP, or how much you've done, where you're heading with it?
So on the AMP, it's still, for us, it's side research. We're not producing a model out of it to generate income. So if I was to put a schedule on it, I get to spend about 10 hours a week when I'm having a good time with it. Where we're heading with it is, I want to solve this. And not just for us internally, I want to solve this and make sure that we have it solved in the demo code that we put out on the GitHub. And when I mean solve it from the point of view of being able to offload this whole array set and have the parts that at least can be calculated in parallel, while we're still handling things, like volume balance and existing income in the way that it has to be done because it depends on the previous value. Yes. Yeah, absolutely. There's certain, a lot of this stuff, there's nothing really magical. Well, I don't want to say there's nothing. There's nothing really that proprietary about calculating an interest rate. You calculate an interest rate. There's nothing proprietary about, how you calculate income. It's income. So yeah, this is planned to be put out. Yeah, no problem. Yeah.
Out of curiosity, have you looked at something like a prefix, some algorithm to parallelize this dependency? Because it sounds like maybe it could help if you have a chain and do operation after operation after operation, and then you need a part of that chain, and then you need the smaller part. But you always need the entire chain of operations for every single one of those.
On a lot of these rows, two of the rows I know have a dependency on the prior month. So that could actually work. And no, I hadn't looked at that. So please, if you don't mind, I'd like to get after. Anything else?
Related to parallelizing, it seems like thread pools might be an interesting thing to look at.
Yes.
When you have a fixed number of threads and just a set of tasks.
Yes. And so we did do thread pools when we started working with the accounts on the SBS. And that's where I was saying we were able to get speed up if we just do with the SBS accounts and testing. We did MP at one point. We also tried doing, well, I said thread pools. It was a manual pool. We set 4 maximum threads, then turned around and fed the accounts through as they came up. And so it was we definitely can get speed ups in the parallelizing. But I really want to hit, to me, this is kind of our holy grail. I'd like to get it to where inside the account instead of just at the account level. All right? Thank you very much.